Now that we've learned how to do a canonical correlation analysis, let's take a look at some stuff we can actually do with it. We looked at some practical interpretations, but there's actually quite a bit that we can do with canonical correlation in addition to what we saw there. So one way to think of canonical correlation is as an alternative representation of multivariate multiple regression, in the sense that both techniques summarize the relationship between two multivariate sets of variables. And in fact, canonical correlation can form the basis of effect size in multivariate multiple regression. So there is no direct analog of R squared in multivariate regression. So to find an alternative that sort of can give us a similar type of information, it helps to define some desirable properties for our sort of multivariate R squared. So it should be bounded by 0 and 1, just like R squared. It should be invariant to linear transformations of the variables, specifically non-singular linear transformations of the variables. It should increase as predictors are added. And it should be sensitive to correlations in the response variables. And so like that last one is a new condition that doesn't apply to univariate R squared, since where there's only one response variable. So a possibility that satisfied these conditions is actually something that we've already seen. So remember that when we were testing the null hypothesis that each of the canonical correlations was 0, we defined Wilks lambda as the product of 1 minus each of the correlations squared. And just like when we define eta squared lambda in the MANOVA context as 1 minus lambda, that should actually be big lambda. I'll correct that. This lambda this is little lambda. I should have made it big lambda. We can define R squared xy the same way as 1 minus lambda equal, which in this case equals 1 minus the product of 1 minus all of the canonical correlations squared. So that's one possibility for an R squared alternative in multivariate regression, but there's another one that we're going to look at. So first, we're going to define Vxy as the trace of this combination of covariance matrix, or slices of a covariance matrix. And these are actually going to be the covariance elements of the covariance matrix between the canonical variates of x and y. So you could actually call these maybe S, U, and V would be better. Like this would be better as SVV or SVU or SUU or SUV. We can then define a p squared as p squared yx in this case. Note that we switched it around, and the reason is because we're saying why the order matters for p squared where it doesn't for r squared. We can define p squared as vxy divided by q, where q is the number of response variables. So both of these measures have strengths and weaknesses. They both will typically satisfy the 4 properties that we're aiming for. They both have a lot of the desirable properties we're looking for, but they both have weaknesses as well. The problem with p squared yx is that it won't work if there are more response variables than predictor variables. So if q is greater than p, in this case, it can never actually reach 1, so it will violate the unit scale condition. On the other hand, r squared xy will never have this issue, but it can be shown that it's not actually a proper additive decomposition of semi-partial correlations. Don't worry too much about what that means. This is another property of normal r squared that won't actually apply to this r squared. It will apply to p squared, but it won't apply to r squared. As a result, when p is greater than or equal to q, as will typically be the case, p squared is going to be preferable. Otherwise, r squared is going to be what we should go with. So one of the other reasons we like these measures is because they can be used for dominance analysis, and indeed can be computed and applied in the dominance analysis package. So everything we learned about univariate dominance analysis applies here. We still fit all possible nested regression models and subsets for our p predictors, and then average the r squared deltas or the p squared deltas at each level, and then average those across levels. And this produces a contribution average for each predictor for the multivariate regression as a decomposition of r squared or p squared. So we're going to go back to the baseball data that we looked at last week for this. The reason is that the worker satisfaction data had more response variables than predictor variables. That's not really a great example to use. In most cases, it's going to be the other way around. And that's what we're going to look at here. So back to the baseball data. Just as a reminder, the variables are first the team, which is not really a relevant variable. This is just for reference, the name of each of the 30 baseball teams from the 2019 baseball season. Second is how many games they won. The third was their average fan attendance for home games. The runs variable is the total number of runs the team scored. ERA is the earned run average, which is the quality of pitching. And then defense is the quality of team's defense, with 0 being average. The model we're interested in uses runs, ERA, and defense to predict wins and attendance. So first, let's run our canonical correlation. And so again, we get our markdown seems to produce a slightly different output than what shows up in my R console. That's okay, we can sort of ignore that here. So first, let's practice interpreting the results of the canonical correlation before we move on to effect size and dominance analysis. So this is the coefficients for the X canonical, the X canonical variates. So how would we interpret these? So this was a bit of a trick question. We wouldn't interpret these. This data isn't standardized, so it's very difficult to interpret these coefficients, these raw coefficients directly. Part of why the coefficient for ERA is so large is because it's on a much smaller scale than runs or defense. Defense is a little cut off here, but the standard deviation is about 40. It's about 90 for runs, but it's only about 0.59 for ERA. So that's why these coefficients are on completely different scales from one another. So they're a little bit difficult to compare directly. To rectify this, we can get these standardized coefficients. So these are much easier to interpret. So how would we interpret these coefficients? So the first variate is driven by runs and ERA, not defense. And the direction for runs and ERA are also opposite. So runs are negative and ERA is positive here. The actual sign itself doesn't matter that much. What matters is that they're opposite one another. And this makes sense since more runs are good, but higher ERA is bad for the team in question. The second variate is driven by ERA and defense more, as well as runs to some extent, but about half as much. It's much more driven by ERA. We can also check the alternate interpretation to check the correlations between the original variables and the variates. It's not necessarily better. I shouldn't say it that way. I'll correct that. This isn't necessarily a better interpretation. This is just another way to interpret the meaning of the variates. So here we can see that the first canonical variate, well, I'll give you a chance to interpret it first. Then on the next slide, the first canonical variate seems to be correlated with runs and ERA. Again, in opposite directions. Again, that makes sense. It's also correlated with defense, though by about half as much. The second seems correlated more with defense and a bit less with runs and ERA. So for Y, here are the standardized coefficients for the canonical variates. And so the first variate is driven almost entirely by wins, almost not at all by attendance. The second is a mix of both, but almost twice as much by attendance as wins. So for the correlations, here are the correlations between the original variables and the Y variates. So the first variate is correlated almost perfectly with wins, but also with attendance, but not by as much. But it's really almost entirely just wins. It's like almost perfectly wins. And so this is, in a sense, a good example because we can see that this first canonical variate is almost just literally wins, but that wins are also just correlated with attendance anyway. So the second canonical variate is much more highly correlated with attendance, but it's almost not correlated at all with wins, which again makes sense since these are orthogonal. If the first one is almost perfectly correlated with wins, the second one, by definition, has to be almost uncorrelated with wins. So now that we've interpreted our variates, let's get back to effect sizes. So again, we can get r squared as 1 minus lambda equal, or 1 minus the product of 1 minus each of the canonical correlations squared. So I can get that pretty easily from my my canonical correlation object. I'm just translating this into R code where I'm getting the canonical correlations out of the canonical correlation object that I fit before. And so this is r squared xy. Getting p squared yx involves a few more steps. First, I need to compute or extract the canonical variates. Then I need to combine them and partition their covariance matrix, compute this vxy statistic. This is not the same as the v variate. This is a statistic, and divide by q. So first I'm going to combine the canonical variates together. I'm just rounding off here just so we can see it a little bit better. So this is the covariance matrix between each of the canonical variates. Note that x1 is orthogonal to x2 and to y2. So the off variates are orthogonal, while the y1 is correlated with x1 and x2 is correlated with y2. These are our canonical correlations, same thing up here. So then I'm going to slice up this covariance matrix the way that I showed before. So we're going to get SXX is just the covariance for the x's. Y is the covariance for the y's. XY is this partition down here, or I'm sorry, it's this partition up here. So it's the rows of x and the columns of y. And this is the rows of y and the columns of x, SYX. So to get p squared xy, I'm going to first generate a matrix as I defined it before, where I'm inverting yy, multiplying by yx, inverting xx, and multiplying by xy. So that's going to be this matrix here. So you can see that the off diagonal of this matrix, again, is also going to be zeros. We're only going to have this is going to be a diagonal matrix. And then the vxy statistic is the trace of this matrix. So I'm going to add up the diagonal elements. And then to get my p squared, I'm going to divide by the number of variables in y. So I'm going to divide by 2 here. And so that's going to give me this is going to be my p squared statistic. So the dominance analysis package has a function that can get us both r squared and p squared. It's called MLM with cove. It uses formula syntax, and it creates an object with both effect sizes. The only kind of funny thing about it is that instead of using the data, you actually have to use the covariance of the data. So unlike when we did the canonical correlation analysis, where we couldn't do it with a covariance matrix, we had to do it with the original data. Here we have to do it with the covariance matrix. So I'm going to load up dominance analysis. I'm going to get the covariance matrix, but I'm going to remember we have that team variable. It was the first one, so I'm going to drop that first variable. And then I'm going to fit an MLM with cove object with formula syntax using the covariance matrix, not the original data. So this is just the covariance matrix. Then I can get my r squared, which will be an object, part of this object. It will have the r squared and the p squared inside of it. So these both match the values that we got before. So these are our r squared and p squared. So last week, we went step by step to compute the contribution of ERA and wins. This week, we also include attendance as a response variable. And we're going to use p squared as the fit criteria, which is the relevant effect size. But the steps here are otherwise identical to what we saw last week. We're just going to fit all the subsets of models, compute the deltas, and then average at each level, and then average across levels. So here I'm going to get when k equals 0, my delta is just the using ERA as a predictor. And so I'm extracting the p squared. So here I'm going to get the r squared for runs and defense, or the p squared. It says r squared here, but they're really p squareds. So then I'm going to get for ERA plus runs and ERA plus defense, and then the deltas are going to be the difference between those two models. So here's with runs and ERA minus just runs, defense and ERA minus just defense. And then do the same thing so we're going to get runs, the model with runs and defense, then the full model with ERA runs and defense, then the delta for adding ERA over runs and defense. So now I have my deltas at each level. I have all the deltas I need. So I get my contributions by level. For k equals 0 and k equals 2, we again only have one model. While for k equals 1, we have two models. So for k equals 0, my contribution by level is just the ERA delta. For k equals 1, I have to average the ERA over runs and ERA over defense. So that gives me my contribution at level 1, and then contribution at level 2. Again, I just have one model here, so it's just the p squared there. And then I'm going to average all of the p squares by level, the contributions by level, and that's going to give me my contribution average for ERA from the full model. And so I can also check the proportion of the contribution average from the full p squared, just like I did last week. So here the interpretation is that when compared to runs and defense, ERA contributed 0.27 to the total p squared of 0.63 of the three predictors on attendance and wins, and it was 42% of the total p squared. And of course, we can just do all this the easy way with the dominance analysis function, and we get the same result. The key here again is that we need to use the MLM with Cove object that uses the covariance matrix rather than the actual MLM object. You can't enter an actual MLM, which is an MLM is just a multivariate LM. So you can't use that in dominance analysis here. The way we did last week, you have to actually use the MLM with Cove object. But the output is going to do the same thing, and it's going to give us results for both p squared and r squared. And so here we see the only result we got by hand was this ERA for p squared, but here are the contributions for each variable for each effect size. And so that's how we do dominance analysis for a multivariate regression.